All right.
Do you guys have any questions over what we were talking about last time? Type 1 error rate, type 2 error rate. Right then, it seems like a while ago that we did this, but the other day I had you go out into the hall and measure some tiles for seemingly no reason. We're going to look at those data today. There are some terms that students regularly misuse because they don't fully understand the meaning of the terms, I think. These are the terms accuracy, precision, and repeatability. Who's familiar with these terms and can give us some definitions? Bryce.
Accuracy is how close you are to what the actual value is and like what the intended result is.
So we talked about this last week. Was that last week? Or was it earlier this week? I just recall. What's precision? When you guys measured things out in the hall and then you came back in, I made you go back and remeasure because you didn't measure, you didn't report your results to the maximum level of precision. For a meter stick, what was the maximum level of precision? Was it a meter? Decimeter? Centimeter? Millimeter? It was a millimeter, wasn't it? So for the meter stick, the level of precision was 1 millimeter. What was it for the laser meter? Do you recall? Yeah, also a millimeter. So the laser meter was also 1 millimeter. What was it for the DBH tank? A centimeter, wasn't it? So precision refers to how finely divided your measurement scale is. I work on the thermal ecology of geckos. When I'm in the field, I have a digital thermometer that I use for measuring environmental temperatures and for measuring the body temperature of geckos. I can set that thing to report data in either degrees centigrade or degrees Fahrenheit. I ask it to report it in degrees Fahrenheit, even though I'm going to have to get back to my office, put it into a spreadsheet, convert it to degrees centigrade. But the reason that I measure it in Fahrenheit is because there are more degrees of Fahrenheit in a degree of centigrade. So it's actually the more precise scale of measurement. And then I can convert it into centigrade, but I'll get a much more precise answer in terms of more decimal points. It's dividing the scale up into finer and finer units by measuring it originally in Fahrenheit and then converting it when I get back. So precision has to do with how finely divided up your measurement scale is. The laser meter, relatively precise, but it's actually no more precise than a yardstick, than a meter stick is, because they're both measured down to a millimeter in terms of their precision. What is repeatability about? Yeah, great.
Like just the ability to repeat the experiment or whatever you're doing, get the same answers.
If you measured the thing over and over and over again, would you get the same answer over and over and over again? So on Moodle, there is a little R script that I had up the other day because I was putting the data in as you guys generated it. Let me clear everything out. So there are a variety of ways in which you can build data sets in R. I typically will build a data set in an Excel spreadsheet or something like that and then import that into R. But you can also just build data sets from scratch within R. And this is kind of how you do it. The first thing that I'm going to do is make sure that I'm in a correct working directory. I am in my computer in the Data Science 218 folder in a subfolder called RScripts. So I'm in the directory that I want to be. It actually doesn't really matter in this case because I'm not importing anything in from anywhere. Because what I'm going to do is I'm going to use this set of commands to essentially build your whole way measurement data set up from scratch. You would not want to do this with large data sets because it's a total pain in the butt doing that in R. But basically, I'm defining two different columns here, or two different strings of data. One string is type, the type of data that you were taking, whether it was with a meter stick, a dBH tape, or a laser meter. So because I know that I have 4 measurements of each type, because there were 4 teams of you, I have meter, 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 dBH, 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 laser, 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 laser. And then the second line here is defining another string that is length. And it's just a concatenated list of all of the lengths. And as you were putting them in, as you were putting them up on the board, I was leaving myself placeholders because the different methods came in at different times. So this is the first meter, this is the second meter, that's the third meter, that's the fourth meter, dBH, 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 dBH. You can tell that those are dBHs because they have only data down to the centimeter level, and then the last 4 here are lasers. And then what I'm basically doing is I'm making a data frame out of these 2 strings. So I'm basically defining a data frame as DAT, and it's going to be a data frame made up of type data and length data, which are these 2 strings of data here, and then that should give us our data set. So when I run those 3 things, it doesn't give me any error messages, and now I have a long form data set. So in R, you can have data sets that are long or wide. Typically, even if I end up getting a data set given to me that is wide, the first thing that I will do is I will convert it to long. And it basically just has a bunch of rows. Each row is a separate observation. 4 observations with a meter stick, 4 observations with a dBH tape, 4 observations with a laser meter. Now what we can do with that is we can do things. So I'll load some libraries. As you're loading libraries, pay attention to what happens down in this pane here. If you get red text down here, those are warning messages from R basically saying, you've asked me to do something and either I couldn't do it or I did it, but in the process of doing things, I did some things that I want you to know about. So error messages in R take 2 forms. There are some error messages, which are in red, that are just merely informational. So a lot of times when you load the package car, it relies on another package called card data. And so it will give you an error message that basically says, you asked me to load car depends upon this other package card data, I'm loading card data also. But that's just merely an informational warning error message to you. It appears in red because R wants you to pay attention to it, but it doesn't mean something has gone catastrophically wrong. On the other hand, you might try to load car and it says, package not found. Well, what that means is that you haven't ever installed that package in your version of R. You asked me to load that. I can't load it because it's not installed. Therefore, you don't have access to that package right now. You need to go and install that package. So when you get error messages, read the error messages and try and determine for yourself, is it an error message where it's just trying to tell me some information, or is it an error message that basically said, I asked it to do something that it can't do? If it's an error message that it's telling you that you asked it to do something that it can't do, you're gonna find that you have problems further down as you continue to try and work because of an error that occurred early on. So when you see those errors that are, something's catastrophically wrong, I can't do the thing that you asked me to do, you need to stop right then and there and figure out what it is that you did or didn't do that is not enabling R to do what you're asking it of. Because I was already running this morning, I'm not getting any error messages because I already solved all of those things. Yeah, happens.
Do you recommend us to download our computers?
If you have a computer and you want to do that, I would recommend doing that. Two things, that frees you up from having to come to this room in order to do your work. And then the second thing is, it just gives you the opportunity to play around with it, back in your dorm room or whatever, without having to come over here. If every time you use R, you have to come over here, log onto these computers and use it from here, then that just becomes cumbersome and you'll make less progress than if you have it on your computer. So R runs on Mac, R runs on Windows, R runs on Linux, so there's no platform that R won't run on. The specifics of kind of the keystrokes that you use for different things vary somewhat from platform to platform, but it'll run on your computer. It's not a terribly large program, which is nice. It gets larger the more packages you're loading up and things like that, but yeah, if you have a computer and you want to put it on your own computer, then by all means do that. One of the advantages of that also is when you come by my office for help because your R script isn't running, we can just look at it on your computer rather than, once again, having to come up here. If we have to come up here and there's a class being offered in here, we can't obviously work on it, here as a result of that. So yeah, by all means, put it on your computer. In the syllabus, there are download instructions for getting R in RStudio. R is a base package. RStudio is basically the graphical user interface that has these 4 panes that allow you to navigate around a little bit better. You can do everything in base R if you want to. I just find it a little more cumbersome to work out of base R rather than RStudio. My partner, who also does quite a lot of statistics, for a long time she was a base R person. She did everything in base R, And she's like, why do you use RStudio? That's stupid, that's just for wimps, et cetera, et cetera. And then I showed her some of the features of RStudio, and she's like, maybe I'll start using RStudio. And now she works out of RStudio constantly, so it's largely a preference thing, but it's also for me an ease of work thing. So I've talked to you about Summary SE, which is this routine that basically calculates summary statistics for a given data set. I usually store this in a new data frame called CI plot, which just stands for confidence interval plot. This is how I use Summary SE to give me the summary data that I use to then make plots. So this is just going to summarize those data. And what you see here is that it's done a couple of things. It rearranges. This is just something that R does by default. It will rearrange factor data alphabetically. So we originally put it in with the meter stick first, then the DBH tape, and then the laser meter. It has rearranged it to DBH, laser, and meter because it alphabetizes things. You can tell R to not do that with a little command that basically says, you tell it what order to treat your factors in. I don't really care at this point because it's not really going to affect the end result. But once again, it gives you the sample size because there were four teams. We have 4 observations of each type of measurement. We have the average lengths. We have the standard deviation, standard error, and the width above and below the mean for the confidence interval. And using these data, we can make a plot. And the plot looks like this. From the standpoint of accuracy, repeatability, and precision, what can you tell from looking at this plot? about the DBH tape, the laser meter, and the meter stick as measuring devices. Yeah, Athos.
The meter stick had lower deviation.
Okay, so it looks like the meter stick has lower variance,
Yeah,
lower,
variance.
less of a difference from measurement to measurement. So the lowest tech version of doing this actually produces a set of numbers that have lower sample variance associated with them, a narrower 95% confidence interval. Are these three means different from one another? If we were gonna statistically test these means, would they come up as being statistically different from one another or not different from one another?
They're all written like the variances of each other.
Yeah, all of these means fall within one another's confidence intervals, with the exception of the DBH tape mean falls outside of this means confidence interval, but overall, because for the most part, they all fall within one another's confidence intervals, you're probably, if you were to run a statistical test on this, which would be an analysis of variance, you would find that these three means are not statistically different from one another. So in a sense, they're all giving you the same answer statistically. The DBH tape and the laser meter are more variable from sample to sample, which is striking because you would think that the laser meter would be most invariant. Why was the laser meter just as variable as the DBH tape?
Because you don't know how to measure.
So I asked you to measure tiles on a floor, right?
Yeah.
What does a laser meter do?
It goes straight. It has an angle, yeah.
Distance from point to point, as long as that's horizontal, as long as you're keeping that horizontal and keeping it straight, should give you very reliable measures. The thing that most people use laser meters for is measuring rooms. And when you measure a room with a laser meter, what you do is you put the flat butt of the laser meter up against the wall, and you measure from this flat wall to that flat wall. And when you're doing that, it's very repeatable, very precise, gives you very good data. You were measuring something that was on the floor, so you had the laser meter at the back end of the tile, and then what did I see you guys doing at the other end of the tile?
Holding up a book.
You guys were doing things like holding up a book. And when you hold up the book, you have to make sure that you're not leaning the book forward, leaning the book back, et cetera, et cetera. That then introduces some measurement error, which is why measuring this particular thing with a laser meter was actually producing more variable results than the meter stick. What did you do with the meter stick? You laid it right down on the brick, right down on the tiles, so you had a much better idea of what the length of those tiles were because of the measuring device that you have. So you can go down to the Home Depot and buy a meter stick for like less than $2. You have a laser meter. That laser meter cost me about $400 when I bought it about a decade ago. Why on earth would I own a laser meter if a meter stick would do just as good of a job?
It's a lot easier to use. It's a lot easier to use. It's quicker.
Actually, that is true in a sense. I bought this because there's a project that I work on in Puerto Rico where we chop down the forest canopy, and I thought I had moved these over to the PowerPoint presentation, but I guess I didn't. Let me go and get something real quick. I meant to do this, and just for whatever reason didn't. PowerPoint for your class. I thought I had copied these over from another class where I teach this stuff. And I guess it didn't. These are the plots that I work on in Puerto Rico. These are inside of a forest, and we have these, like I said, we have these 20-meter plots where we do our measurements, but the plots themselves are 30 meters, so that we have this 5-meter buffer around the plot, and for whatever reason, this figure isn't coming up. Oh, there it is. So these plots, these 20 by 20 meter plots, are gridded off into plots that have different functions. And so I work on animals, and so there are a set of plots that are available for measuring litter decomposition, seedling regeneration, et cetera, and because there are like 23 researchers working on these plots, you don't go into other people's subplots. So I was allowed to go into this plot, that plot, and that plot to make measurements of litter arthropods. And there are trails that go between these plots. And so you don't just, if you come into a plot from the trail that goes to the plot, you don't just get to the plot here and then cut across to get to your plot that you need to go to. You go down the edge, and then you cut in, and then you cut over to get to the plot that you're going to. And the whole point of having these trails is the people who study soil chemistry don't want you tromping all over their soil, because that messes up their data. And so I was restricted to these trails in order to measure my data. One of the things that I was measuring is I was measuring the densities of lizards that live in these plots, and I was measuring the density of frogs that live in these plots. And when you're measuring density of animals, one of the ways you can do it is to mark the animals and then recapture them and do that over and over again. And the longer you do that, the more animals you've marked, and you reach this point where you can calculate on the basis of the ratio of marked to unmarked individuals that you catch each time, you can figure out what the population size is as a whole. But because I couldn't walk into the plots, I couldn't mark and recapture them. So I couldn't ever actually grab the lizard, because if I was walking along the trail here and I saw a lizard here, I can't walk into that plot, grab him, mark him, release him, and then recapture him at a different time. But one of the things that I can do is, as I'm walking down this 20-meter transect, if I can record the distance from the transect to the lizard itself, I can create a distribution of detection. So I can plot if 0 is where the trail is, and I have a lizard at this distance, a lizard at this distance, a lizard at this distance, a lizard way out here, et cetera, et cetera. I can use the detection distances to plot a frequency distribution around the center of the transect that tells me kind of what's the detectability of this particular species of organism. From that, I can then do some statistical machinations that will allow me to give an estimate of population size based on how many lizards I'm finding, how far away they are from me, and what the detection decay is as you get further and further away. Obviously, it's harder and harder to detect these little lizards that are really tiny. So when I first went out to do this and try this, I just took a regular tape measure from the hardware store out. And the thing about a tape measure is it's relatively precise, but as you feed it out, it's metal, and you get to a point where it's out there far enough, it just bends over and falls to the ground. So once you were beyond like 2 meters out, it was impossible to measure the distance of the lizard from the trail without going into the plot. And the whole thing is you don't want to go into the plot because that messes up other people's data. So what I did was I bought a laser meter so that I could just stand here, I could shine the laser on the lizard's body, and it would tell me how far away I am from the lizard. So I could get the distance data that I needed. It cost more than a metal tape measure from the hardware store, but it did the job that I needed it to do. It did it better because a light beam doesn't kink over and fall to the ground on the weight of the lizard. So that's the reason that I used it rather than something else. So sometimes we spend money on more expensive things, not because they're any better at measuring than some other method, they just happen to be better in that particular instance. For measuring tiles on a floor, a meter stick was actually more repeatable than the laser meter or the DVH tape. Once again, we can look at this by just showing you the data jittered, but this doesn't tell you anything about where the means are, but you can also do this where you have the data jittered, but you also have the mean, and then you also have the 95% confidence intervals that are displayed. It doesn't really matter how you display the data, you can display the data any way you want to, but one of the things that you see is that there's less variability here, more variability here, and more variability here. Fairly repeatable, less repeatable, less repeatable. Even though this is less precise, it's still just as repeatable as this thing that is more precise. And so make sure that when you use terms like accuracy and precision and things like this, that you're using them appropriately. They all refer to different things. I could have given each of you a dowel that is a meter long and said, record the width of those tiles to the level of precision that this measuring instrument gives you. And because it's a 1 meter long dowel, the level of precision that you can give me is in 1 meter increments. You can't give me anything lower than that because the measuring instrument isn't divided up that finely. As a result, we would have gotten a lot of highly inaccurate but highly repeatable data because you all would have said it's 3 meters because that's the measurement increment that you have available to you. So while it wouldn't have been as accurate as some of the other methods, it would be highly repeatable. All of you would have given me the same answer rather than a bunch of different answers. If you're measuring a room to lay tile, you want more precision than that, don't you? And you want more accuracy than that. But for some things, precision and accuracy are less important as much as repeatability is. In ecology, once again, this is something that I meant to have in today's PowerPoint. I thought I copied them over, but I didn't. In ecology, sometimes we want to know what the plant community is about. You know, what kinds of plants are there and how many of them are there. Well, there are a variety of ways of doing this. One of the ways is using a thing called a Daubenmeier frame. A Daubenmeier frame is simply a PVC frame. It's painted, and it's painted, and Bryce is looking, you've used one of these, haven't you?
I have.
Yeah. A Daubenmeier frame is painted such that there's a white section here that's a quarter of the total area, a black section here, a white section here, a black section here. These represent a quarter of the area, and then one corner is painted in such a way that it makes up 5% of the area. And so you then divide the vegetation that you see. So what you do is you take this piece of PVC out, this PVC frame out, you put it on the ground in the prairie or whatever that you're measuring, and you put vegetation into different cover classes. One cover class is 0 to 5%, 5 to 25, 25 to 50, 50 to 75, 75 to 95, 95 to 100. The midpoint of these ranges are here, and that's ultimately what you end up analyzing. But what you do is you basically visually find a particular species and you gather it up and you ask yourself, if I take that plant species and I gather up all the plants that are in this frame, would they fit in this little area, or are there more of them? Do they fit in this area but not extend into this area if I gathered them all together into one part of the frame? And in this way, you have a visual guide, which is the frame, and you can kind of mentally say, there's a plant here, plant there, plant there. You place the Daubenmeier frame and you say, okay, here's a species. In terms of coverage here, if I took this plant, this portion of the plant that is in the frame, this portion of the plant that is in the frame, does it fill up 5% of it? Does it fill up 25% of it? does it fill up 50% of it? Well, this, and this would fill up more than 25, but not more than 50. So it's in the 25% to 50% cover class. Not terribly precise, but you give a Daubenmeier frame to a person, set it down on the ground, have 10 different people come by and put plants into cover classes, they're all going to do it very repeatably. Part of the repeatability of this method for measuring vegetation is the fact that it's not terribly precise. But if all you want to know is what's the relative abundance of different plant species compared to one another, precision is less important than perhaps repeatability, especially if you're going to do 100 of these plots with 10 different researchers. You want to reduce the person-to-person error that comes into your data this way. So when you're measuring, when you're making measurements, it's good to think about how important is absolute accuracy. How precise does my measuring instrument need to be? Generally, the more precise something is, oftentimes the more expensive it is to do those measurements because you're wanting a particular level of precision. And how repeatable do you want your measurements to be? My first job in research was as an undergraduate, and I was at Stephen F. Austin State University in East Texas, and there was a place called the Stephen F. Austin Experimental Forest out of town a little ways, and this was back in the days when acid rain was an issue that people were concerned with. That's how old I am. We don't even teach about acid rain now in environmental science classes because it's largely not a thing in the United States anymore. But acid rain and ozone were two things that were critically important to researchers back then because back in the 1980s we had a much more polluted environment than we do now. So I got a job out of this forest plot where they had built these structures. It looked like a colony on the moon. They clear cut this forest. They put up these structures that were made out of metal with plastic wrapped all around them. They had these air circulators outside, and I got paid to mix up gigantic batches of acid water at different pHs, and then I got the job of measuring seedlings. So there were pine seedlings growing inside of these enclosures, and these enclosures were being watered with different pHs of water, and the air was blowing different concentrations of ozone into them so that we could look at the effect of ozone and acid rain on tree seedling growth. But the way that we measured seedling growth was you have a little tiny seedling pine coming up out of the ground, some little branches coming off of it, and they gave us a little standard piece of PVC. And what we would do is we would put that PVC down on the ground next to the trunk of this growing seedling, and they gave us a pair of calipers, digital calipers, very nice, easy to read, very quick, and we would basically close the caliper around the stem of the seedling and measure what the diameter of the seedling was, because there are equations for commercially available plant species that basically, if you know the diameter of the tree at a given height, then you can calculate how much biomass is in that individual. So you would put the caliper on here and you would measure the diameter at this point right there. Let's say that that's the width of the jaws of a caliper. Well, I was actually taking my undergraduate introductory statistics class when I was working here. And so I decided that what I would do is I would measure each seedling that I measured not one time, but 4 times. I would measure it once where the jaws closed this way. I would measure it once where the jaws closed this way. I would measure it once where the jaws closed this way. And I would measure it once where the jaws closed this way. I kept the first data point that I recorded, and that's the one that I turned into the guy who was in charge of this project. And I kept all the other data points to myself. And then I went and I analyzed them. And what I found was that there was as much variation from measurement to measurement on the same stem as there was from one plant to another in a given little house of trees, little seedlings. After I did this, I went to the postdoc who was in charge of this project and said, we should rethink how we're measuring the size of these seedlings because it's just really messy data the way it's currently being done. These are little seedlings, so they're soft, as opposed to a big tree where the wood is harder. So if you squeeze a little too hard or don't squeeze quite so much, they're not perfectly round, so if you measure it on the narrow side rather than the big side, like there's just a lot of measurement error in the data that you are getting. And I have the numbers here, I have the data here to prove it. Guess what? He was really not interested in some little undergraduate calling into question the veracity of his data. So I finished out my summer stint, my summer job at the tree farm, and went back to the biology department and went on with my life. But I always wondered what came out of that project and what they did with the data, et cetera, because at some point the seedlings got big enough that the seedlings would have been a big enough diameter that these minor differences in measurement wouldn't actually matter. But at those really young seedlings, it was enough that it probably obscured any differences. Measurement error obscured any differences that you might have been able to see in their experimental treatments. And so this was my first introduction into, in this case, the idea of repeatability. Send 10 people out to the same plot to measure these seedlings, you're going to get a lot of measurement error from person to person, because I got a lot of measurement error within one person measuring the same seedling multiple times. Messy, messy data. So it's something worth thinking about how it is that the data were collected. In the springtime, our seniors in chemistry and biology are finishing their senior research projects. A certain proportion of them every year come to me to get help analyzing their data. The first thing that I do is I sit them down in my office and I get them to describe to me what it is they did. What was the question that they had? How did they analyze the data? How was their experiment set up if they did an experiment? Because I, as a statistician, need to know all of the particulars about this if I'm going to make wise choices about my advice to them about how they should go about treating their data. And so the method by which you collected the data sometimes can become important because that gives you some insight into how repeatable these data are. If we went and did this again, would you get the same result that you got before the one time you did it, or would it give you a different result? Not because the biology or the chemistry of the system is different from time to time, but it's just a matter of, is there error built into the way in which you conducted the experiment? If that's so, then there's going to be more error, more measurement error in the data that come out of that, and we need to know about that. I'm eventually going to see it when we plot your data, but if I can start thinking about it early on, I can begin to think of ways in which we can deal with that. Ultimately, looking at the 95% confidence intervals, we can do an analysis on this, and the analysis of variance basically shows us that the p-value is not lower than 0.05, and so we would not conclude that these three measurements are different. And we shouldn't be surprised because they're tiles on a floor, they're rigid, they don't fluctuate a lot. The only thing that's fluctuating here is measurement error. And so when we think about error, the type of error that we're oftentimes thinking about is measurement error. How much variation is there in our data because we measured inconsistently, et cetera, et cetera? How much randomness is there in the system because of measurement error? Questions?
For the R, third line from the bottom, it's given kind of the title headers. It says PR, parentheses,
Oh, yeah.
graded F. if it calculated to be less than, does it actually print PR parentheses less than F? Know what I mean?
No,
Okay.
no, it
Okay,
gives, this
so
is.
we just need to commit to our memory, we're looking for a PR less than F.
Had it been P is 0.04, remember P is the observed type 1 error rate. And you always compare this to alpha. And if your observed type 1 error rate is lower than whatever you set as your alpha level, you would conclude that the differences that you're observing are significant. If it's higher than your alpha level, then you would conclude they're not different. Because you have basically said up front before you did your experiment, I only want to make a type 1 error 5% of the time. Based on our data, if you say that those data are different, you would have a risk of a 4% occurrence of type 1 error. So because you said you don't want to make it any more than 5%, you have the risk of making it 4%, you would conclude that we've passed our criterion of type 1 error and can say that they're different.
Could you do me a favor and draw that on one of those little things?
Yeah, so like a distribution.
Yeah.
So if we have a distribution of sample means, where the population mean is here, and this is the distribution of sample means. Basically, 1.96 standard errors out to the side, if you have an infinitely large sample size, represents the 95% boundary, where 95% of your sample means are in here, 2.5% of your sample means are out here, 2.5% of your sample means are out here. And so what we're saying is if we observe a mean, does the sample mean that we observe fall in here, or does it fall out here? That's the boundary. If we cross that boundary, we would say that's an extreme enough mean that we would say that it doesn't come from the population, the underlying population, that some other mean came from. If it falls within that range, we would say that mean could have come from that same population. We would conclude that they're not different. So when we ask about the difference between two means, we're basically asking, are these two means different? But another way of saying that is we're asking, could both of these means been drawn from the same statistical population, or were they drawn from two different statistical populations? Well, because the distribution of sample means gives us insight into what the population is like by comparing means using the central limit theorem, using the rules about the shape of normal curves and what that means for the distribution of sample means under that normal curve. We can basically ask, could these two means have come from different populations, or is it more likely that these two means came from the same population? That's really the question that we ask when we say, are these two means different? What we're really saying is, could this mean have come from the population that generated this mean or not?
So, what's that? F is alpha, or F is half of alpha?
No. So we haven't gotten to this yet because we haven't gotten to ANOVA and things like this.
Okay, so where is P? P is just on that line, coming across, it's wherever we calculate it.
It's wherever
to
we
be.
find it, yeah. So in this case, our P was 0.101, it's somewhere over here.
Okay.
Because 0.05 is here. And so it's not over that line.
Okay, got it.
0.04 is right here. And so that's over the line, we would say that's different. So F, so we have, we're jumping ahead a little bit.
Okay, sorry.
Remember, no, it's fine. Remember I said that sums of the squared deviations from the mean is one way in which we look at the dispersion of the data around the mean. Sums of squares is the sum of the squared deviations of the mean. When we calculate sample variance, it is the difference between each of the values and the mean squared, summed up across all of the values. This is sum squared, which is that thing. We divide sum squares by whatever the degrees of freedom are to get the variance. The mean squared is just the sum of squares divided by the degrees of freedom. So you can think of the mean squared as just being a measure of variance. This is the mean squared that is the difference between each of these sample means and the grand mean of the entire data set. That's what type is, mean squared treatment. Residuals is the difference between the grand mean and all of the individual data points. Sorry. The residual is the difference between the sample means and the data points for each given treatment. And so this is the mean squared that is explained by the treatment effect here, divided by the mean squared of the variation within the sample. And mean squared treatment divided by mean squared residual is the F value. The F value is what you actually evaluate at 2 degrees of freedom for the treatment and 9 degrees of freedom for your error. And you evaluate that at that point to get what your value is and whether or not that's significant. We'll talk about this all in great detail when we start talking about comparing means. But it's always a ratio of how much variation is accounted for by whatever your statistical model is, divided by all of the variation that's not accounted for by that model. And it's that ratio that matters. The more variance that is accounted for by differences between the means, the bigger this value gets, because the means are different. And as a result, the bigger F is, the smaller P is, and the more likely you are to the means are different. Athos, you had a question?
When are we starting working with R?
When we start doing real things.
Yes.
Right now, we're talking about theory.
Yeah.
So we'll get more R than you probably will care to start.
I feel completely lost. Like I
On
don't
what?
have, like homework wise, like agenda. I don't know. I mean,
So I gave you an R script to do the coin flipping.
I couldn't use it. I don't know.
Why did you not come and see me?
I'm in seasonal practice for 2 hours in the afternoons and nights.
Okay.
I can't. I really can't.
Brady came by and saw me yesterday. What did we do?
We went over everything, or not everything, but a lot.
We figured out something that you were having problems with in R. If you're having difficulty with R, come by and see me. There's going to come a point where you're actually going to be writing your own scripts and things like that. That's when we start actually doing statistics. Right now, we're building the theoretical basis that is the basis of being able to do statistics. Learning the stuff that we're learning now is important for you doing everything after this. If you understand central limit theorem really well, if you understand what the distribution of sample means is, what that means for doing things like constructing confidence intervals, we're going to be using confidence intervals the rest of the semester. You can build a confidence interval around a mean. You can build a confidence interval around a slope of a regression line. This idea that a confidence interval relates back to a distribution of a sample statistic. That's fundamental to making decisions in statistics. If you don't get that now, we're screwed for the rest of the semester, which is why I'm taking as much time on it at the beginning. So relax on R. I've given you scripts that do most of the work for you for the things that I've asked you to do, and just ask you to make minor modifications to them. If you're having trouble even with those minor modifications, or if you're just having trouble to get R to run at all, come and see me. Because, Brady, what was the problem with you running R?
Some error messages.
That were related to not having a particular package installed. That's an easy fix. That's not an R scripting issue. That's, you aren't having to script anything, it's just that you have a version of R on your computer that's not complete yet. That's an easy fix. The most common R mistake that students make at the beginning is they're running R in one directory and their data are in another directory. And they haven't told R how to go and find the data. Which is why I put my scripts and my data all in the same directory, generally speaking. So relax, data science student, we will get to scripting in R soon enough. We're just not there quite yet. Other questions? Tom, did that help? With
Yep, but we're gonna hit this again in.
We're gonna hit this so many times,
Okay,
you're gonna be
good.
sick of it before it's all said and
Oh,
done.
yeah.
All right. Other questions? All right, yeah.
If, I went to download art and actually it just sends me on a loop, so it just has me re-download it
Oh.
every single, like, every time I go to open it, it's literally just a loop.
That's dumb.
And I don't know if it's.
Combine.
Okay.
Combine sync,
Okay.
we'll be able to figure it out. So if you want R on your computer, by all means, put it on your computer. If you're having trouble getting it onto your computer, Combine will figure that out. I don't know why it would be doing that, but.
Maybe it's something that clicks when the download I chose.
Who knows? The best thing to do is bring your computer in, we'll set up my table in my office and we'll figure it out. There has yet to be an R issue on a student computer that I haven't been able to figure out, given enough time and effort. Most of the things are pretty easy to figure out if I just stop and look at the error messages that are going through. All right. Other questions? All right, we need to talk about distributions. And you guys are probably thinking, we've already been talking about distributions this whole time. But now we're actually going to start doing statistical tests. So here very soon, we're going to actually start writing some basic scripts that allow us to do certain things. Unfortunately, R is not chi-square test friendly. I can do chi-square tests on a piece of paper by hand almost as quickly as I can set up a script in R to do the same calculation. With all things, the first thing that we're gonna do is we're gonna do hand calculations and then we're gonna do things in R. But we will certainly write a script for this. So chi-square tests and normality tests all fall into a general category of tests referred to as tests of distribution. And the question that you're asking is, let me see if I can see this better. So distributional tests basically ask the question, is the distribution that I'm observing, is that similar to some theoretical distribution, like a normal distribution, or is it similar to some other distribution that I've also observed? So it's asking questions about the shape of distributions. There are a variety of ways in which we can do this. The way that I'm going to teach you for categorical data is the chi-square test. Chi-square tests are complicated because this type of question is sometimes referred to as a goodness of fit test. To what degree does my observed sample, does my observed distribution fit some other distribution? But there are also chi-square tests that are chi-square tests of what is known as homogeneity and chi-square tests of independence. The first one of these that we're going to cover is the chi-square goodness of fit test. Homogeneity asks basically, are the categories of my data similar to one another or not? Are the frequencies the same across some kind of classification? And the chi-square test of independence asks if the frequencies are dependent upon one another or are they independent. It turns out that the way that you calculate these two tests is exactly the same. The way you calculate this test is different.
Frequencies of what?
Of things that you observe. So, let's say that you're a geneticist, and you're an old geneticist, you're Gregor Mendel, back in the 1850s, and you have crossed plants, and after crossing the plants, you get the seeds, you plant those seeds, and then when you plant those seeds, you phenotype them. You basically figure out what their appearances are. And in Mendel's peas, he looked at the shape of the seeds, and the seeds could be either round, which is what you normally think of when you see garden peas, when you see sweet peas at the store. They're usually nice and plump and round, as opposed to wrinkled. If you're studying genetics, you know that from basic Mendelian genetics, that if you cross two pea plants that are producing round seeds, but they have two different alleles for a gene, you should expect to get 3/4 of your offspring population should produce round seeds, and 1/4 of your population should be wrinkled seeds. And so this would be a situation where we're comparing our results to some theoretical distribution. The rules of genetics say that we should have a certain expectation out of doing this cross of different plants with one another. And we're going to use that theoretical distribution to see if the distribution that we actually observe fits that theoretical distribution or is different from that theoretical distribution. So when he did this, he observed 5,474 round plants, 1,850 wrinkled plants, 7,324 plants total. Now, this is the observed. Remember that when we calculate a chi-square test, it is the observed minus the expected squared, summed up across all the categories. In this case, we only have 2 categories, divided by the expected value. Well, what is the expected value? How do we get the expected value in this case? We've already played around with this with incarceration data. The expected data are what we would expect if this theoretical expectation is true, right? So what would we do? We would take 3/4 and
Times 732.
multiply it times 7,324. 1/4 times 7,324. As it turns out, that those values are 5,493 and 1,831. You can see that this is really not that different from that, and this is really not that different from that. So just on the basis of looking at the numbers, you might assume that what Mendel observed is relatively close to what you would expect if Mendelian genetics were actually correct. Well, the way that you test this is you subtract the expected from the observed, you square it, you divide it by the expected. For this value here, it would be 0.06572. For this value here, it would be 0.19716. And this thing summed across the 2 categories that you have is 0.26288. So what you're basically doing here is you're taking 5,474 minus 5,493, whatever that difference is, you square it, and you divide by 5,493. You add that to 1850 minus 1831 squared divided by 1831. This value is that. This value is that. You sum those 2 things up, and that is 0.26288. And this is the chi-square statistic for this test. Now, what you do with that chi-square statistic is you go to a book of statistical tables, you turn to page 24, and when you turn to page 24, it gives you what the chi-square values are that you would need to cross in order to be significant. So let's pull that up actually in a way that you can see it.
So the table value is gonna give us a hurdle rate, is that a plain language, it's gonna give us?
It's gonna give us the boundary that we compare our result to decide whether or not these two distributions are similar or not.
But it's a boundary, but what are we looking for, to go above it or below it?
You want to have something that is above it in this case. It's different from the Shapiro-Wilks test, which is a little weird because you're looking for something below it. I will always tell you whether you're looking for something more extreme or something less extreme. So chi-square test, chi-square table. So just like we've done before with the t-table, you can go and find the chi-square table anywhere. On the internet, I have a table of a book of statistical tables that just has all kinds of statistical tables in it. But here's a chi-square table. Go away. And our degrees of freedom for this test is 1 minus the number of categories. So if the number of categories is illustrated as n, it's n minus 1. So we have 1 degree of freedom for this test. So what we would do is we would go over 2.05, we would go to 1 degree of freedom. We need to compare our observed chi-square test, chi-square statistic, with the table value of 3.841. And we would ask ourselves, is our chi-square value bigger than the table value? If it is bigger than the table value, we would say that the observed distribution is different from the expected distribution. If it's lower than that, we would say that the observed distribution is not different from the theoretical expected distribution. So you can see that as the observed values get further and further from the values that you would expect, this number gets bigger, this number gets bigger, and you get closer to crossing that boundary. So chi-square tests, when you look at the chi-square statistic, large chi-square statistics generally mean that you're going towards significance. Small chi-square statistics means that you're not. Because the number of categories that you're looking at, as they get bigger, you're adding more things together. The criterion for crossing that boundary gets bigger and bigger simply as a function of the fact you have all of these categories wrapped up. We'll work through some more examples on Monday. If you haven't read the first part of chapter 14, definitely read that. We're going to do a lot of hand calculation on Monday, so come prepared with pencil, paper, calculator, whatever. We're going to be cranking through a bunch of numbers by hand. Yeah.
Did you receive my calculator?
I don't know, I'd have to look at my email. I received a bunch of your point flip. If you turned it in digitally, I don't need a hard copy, but if you have a hard copy for me now, I'll take that.
I said it.
Okay.
Thank you.
I got a number of them, I just haven't written down who sent me.
Imagine so many files.
It is Friday already. Yeah.
Okay, cool.
He was just like,
Oh, yeah, you're talking about. Okay, yeah, that's awesome. Okay. Yeah, alright, dope.
yeah.
Have a good trip. Have a good match. Set, is that a set? There's a match. It's a match. Have a good match.
At those, come by and see me if you're having trouble with those. If my office hours don't fit with your schedule, then make an appointment outside of office.
Yeah, I'll try it. It's pretty hard. I mean, I'm in the classes that have weights, then we got.
I have all day free on Thursday. I don't have office hours then, but I don't have any classes, I don't have any labs, so I'm free
Thursday, looks
from
good.
8 o'clock in the morning until whenever I decide to go home. But if I know that you're coming, I'll be sure to be there.
Okay.
What's up?
I'll let you know. Thank you, Doctor.
Yeah, sure.